Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist, where real chemistry happens. That's what we're doing here, folks, where real chemistry happens. All right, so today, what are we doing? We are doing the Periodic Trends Review Worksheet. Periodic Trends Review Worksheet. Prior to watching this video, you certainly need to watch my lecture on this topic, and you need to do all the prior worksheets associated with this unit. So here they are. Well, certainly you need to watch the unit lecture. This is the unit lecture right there. Please watch my YouTube video on that, on periodic trends, general chemistry. Then the first worksheet is right here. That's the basics of the periodic table. The next worksheet is basic periodic trends worksheet. Please watch that video. And after that would be the next video on how to recognize periodic trends of metals and nonmetals worksheet. Please watch that video. The next video is how to recognize periodic trends of groups and valence electrons worksheet. Please watch that video. And then finally, how to recognize periodic trends of ions worksheet. So in order to actually do the video that we're doing here, you need to have watched the lecture. You need to have done the other previous videos and worksheets. So make sure that you do those prior to doing this one. This is kind of like an overall summary of the whole thing. Again, you are watching the Crazy Hat Chemist, where real chemistry happens. And please like, subscribe, and you'll be learning. So what do you need for this worksheet here? What you need is a periodic table, and I'll zoom on out. And this is the periodic table that we'll be using here for this activity. And here it is right here. This is the periodic table. And so there's lots of information incorporated in this periodic table. We'll be discussing some of it, not all of it, because there's so much information on it. All right, so you need a periodic table with you. You need a working human brain. You need to be able to have watched those previous videos and done those previous worksheets in order to understand what's going on as well. So here we go. Question number 1, which element in each pair has the larger radius? So larger radius. So what we're going to do is we're going to go back to our periodic table, and from that periodic table, we're going to figure out what the periodic trend for the radius is. And radius, you can replace this word radius with size. Okay, so which element in each pair has the larger size? Radius, size. So this is the radius right here from this point from there. That is the radius. So which one has the larger radius? Atoms are spherical. And so let's see what we can do. We're going to pull out a periodic table, and then we're going to write down what the trends are in terms of size. So what are the trends in terms of size? So the trends are in terms of size is as you go down a group, the atoms get larger. So as you go down a group, they get larger in size. So this is a size and smaller. So smaller in size, up higher, and larger in size as you go down a group. Then the next trend is across a period. So the trend that all textbooks discuss is that as you go to the right within a period, these are horizontal sections. As you go to a right within a period, this size decreases. So smaller and then larger. So what we're going to do is we're going to flip that around, and since this is larger here and that's smaller here, then actually what happens is the size increases as we go to the left. But going to the right is the trend that you follow all textbooks. That is, as you go to the right, they get smaller. But we're going to take that arrow that's going to the right, and we're going to flip it around just like this. And then we're going to say that they are larger in this direction. You still see that the word larger is over here to the left. The word smaller is to the right. So those are our trends in terms of size. Okay, so that's crucially important to answer this question. So what we're going to do is we're going to figure out what elements we are discussing here. So what two elements are we comparing? We're comparing lithium or sodium. So what we're going to do is we're going to find out where lithium and sodium are on the periodic table. And this 3 right here lets you know where lithium is on the periodic table, and this 11 lets you know where sodium is on the periodic table. These are following the AXZ, that Z is the atomic number. This is standard nuclear notation. So 3 for lithium, 11 for sodium. So I'm going to find element number 3, and that's lithium, and then element number 11, and that is sodium. So which one is larger out of the two? So which one? So they're on top of each other. That means that they're in the same group. So the one that is farther down is the one that's larger in size. As you can see, larger farther down the group. So which one is larger? Well, the answer is going to be sodium in comparison to lithium, right? Fantastic. Now we're going to do the next one. Again, we're following the same pattern here. We're going to follow and find out where element number 12 is. That's the atomic number, and element number 38. That is the atomic number. That's the Z. So 12 and 38. 12 is right here, and 38 is right here. So of these two elements, I have the choice of either magnesium, and we can just make sure and verify that, magnesium, or I have the choice of strontium, right there like that. And again, the trend is as you go down a group, they get larger. So the one that's further down of the two, that is the larger one. So that would be strontium. So what is my answer? Strontium is my answer as which one is larger in size. We're going to do the next one here, and that is element number 19, which is K, and element 35, which is Br. So element number 19 and element number 35. So we're going to zoom on out on our periodic table just a little bit. So element number 19, that's potassium right there. And 35, that's bromine right there, just like that. So hopefully that makes sense where those are located. Okay, so now that I have where potassium is and where bromine is, I'm going to follow their periodic trend. And we're asking which one is larger. And so as you go to the right within a period, they get smaller. Therefore, the larger one is further to the left, and that is element number 19, potassium. So zooming on in here, you should see that element number 19, and that is potassium, is the correct answer for that one. All right. Then the next one that we're going to discuss here is element number 55, that's cesium, and element number 82, that's Pb for lead. So let's find out where those two are on our periodic table. So we can actually fit this right here. So here is element number 55, that is cesium, and element number 82, that is lead. Which one is larger? Well, they're within the same period. And remember, as the farther you go to the left, the larger they get. So cesium is going to be my larger of the two. Cesium is going to be the larger of the two right there, just like that. All right, so which element has the larger radius? Well, it is certainly sodium. Which one has the larger radius of sodium or lithium? Which one has the larger radius of magnesium or strontium? Is certainly strontium. Which one has the larger radius between potassium and bromine? Certainly potassium. And which one has the larger radius, cesium or lead? Certainly cesium. And these two at the top, A and B, were within the same group. As you go down the group, they get larger. And then as you go to the left within the period, C and D, they get larger. And so those are the trends of which that's following. All right. Now what we're going to do is we're going to answer the next question. That is question number 2. Number 2 says, which element in each pair has a greater first ionization energy? So ionization energy, it's usually denoted by just IE. Okay, and we're going to be doing the same thing that we did on the last problem here, and that is we are going to find element number 3 and element number 5. So I'm going to get a new periodic table. We're going to label this new periodic table with ionization energy. Okay, so ionization energy. And so let's zoom on out, and so that we've got this entire periodic table right here. So for ionization energy, the values increase as you go to the right within a period, and they increase as you go up within a group. For the most part, the ionization energy is largest in this upper right-hand corner here, just like that. Okay, so that is the trend for ionization energy. Ionization energy is increasing as you go to the right within a period and increasing as you go up within a group. And so fluorine would have a very high ionization energy, in other words. So let's see what we got. We got two here that we can do, and let's see what we got there. Okay, so what we're going to do is we're going to take a look at lithium or boron. So that's element number 3 or element number 5. So let's pull out that periodic table. We're doing element 3 and 5. See if we can get those on the same page here. Here we go. There's element number 3, lithium, or element number 5, boron. The question is, which has the greater first ionization energy? So we're looking for the one with the larger first ionization energy. So again, the ionization energy, the lithium and boron are within the same period on the periodic table. So as you move to the right, it increases. So therefore, boron would have the larger ionization energy. Let's circle that. Boron has the larger ionization energy compared to lithium, since boron is further to the right within the same period. Let's go for the next one. That's element number 12 or element 38. That's magnesium or strontium. And let's see, here we go, magnesium or strontium. So magnesium and strontium, that is right here. This is element number 12, that's magnesium. Element number 38, that is strontium. So the periodic trend in terms of ionization energy is it increases as you go up a group. So that one, the further one up higher within the group has the highest first ionization energy. That would be magnesium compared to strontium. So magnesium is your answer as opposed to strontium. Yes, perfect. Beautiful, just like that. All right, so the next one here is between element number 11, sodium, and element number 55, cesium. So element number 11, that is sodium. And element number 55, that is cesium. Which one has the larger first ionization energy? Well, as you go up a group, they get larger. So therefore, sodium will have a larger ionization energy than cesium. Sodium will have a larger ionization energy than cesium of the two. Beautiful. Now our next one here is element number 20, that's calcium, and element number 33, that's arsenic. So these two are within the same period. So let's see, let's zoom on out just a little bit so that we can get both of these in here together. So we have calcium, element number 20, or arsenic, element number 33. And the trend for ionization energy is as you go to the right, they get larger. So they're in the same period, same horizontal section on the periodic table. So arsenic will have the greater first ionization energy compared to calcium. Perfect. There we go. I've highlighted those. That looks fantastic. All right. So our next one here is which has the higher electronegativity value of the pair. The symbol for electronegativity is this scripted X, just like that. So what we're going to do is we're going to pull out our periodic table, and then we're going to write another periodic table, but this one will be in terms of electronegativity. Okay. All right, fantastic. So here we go. Here's our periodic table. This is electronegativity. Electronegativity. So electronegativity, how is that similar or different than some of the other trends at which we have followed thus far? So really, electronegativity follows the same trend as ionization energy. That is, It increases as we go to the right within a period and increases as we go up within a group. So the value with the highest electronegativity value is actually fluorine. All right, so let's take a look at the problems of which we have at hand here. And so let's zoom in on this here. So which has the larger electronegativity value of each pair? So we have either fluorine, element 9, or chlorine, element 17. So let's find out where those two are. We have a choice of fluorine or chlorine. That's element 9 and 17. And so the pattern of electronegativity, as you go up the group, they get larger. As you go up the group, they get larger. So fluorine is our answer. Fluorine is our answer for which one has the higher electronegativity value. Perfecto. Awesome. All right. The next one is between element 6, that's carbon, and element 7, that is nitrogen. So element 6, let's see if we can put that here on the screen. Element 6 and element 7. 6 is carbon, 7 is nitrogen. And our pattern in electronegativity is as you go to the right, it gets larger. So as you go to the right, it gets larger. So nitrogen would have the larger electronegativity of the two between carbon and nitrogen. Nitrogen will, because it's further to the right. So nitrogen will have the larger electronegativity value of the two right there like that. All right, perfect. And let's see if we can do the next one. The next one is between element 20, that's calcium, and element 33, that's arsenic. And so let's see if we can get arsenic and calcium on the same page here. Element 20, that is calcium, and element 33, that is arsenic right there. And which one has the larger electronegativity value? The one that is further to the right of the two, that is arsenic. Piece of cake, simple, simple. Arsenic is further to the right. That's following that same pattern. Which one has the larger electronegativity? All right. The next one is between element 8, that's oxygen, and element 34, that's selenium. So we're going to find oxygen, that's element 8 right here, element 8, and element 34, that's selenium. And the value of electronegativity increases as you go up. So oxygen is going to have the larger electronegativity of the two. Since it's higher up, oxygen is going to have the higher electronegativity of the two since it's higher up. All right, fantastic. Hopefully that worked well for you. All right, so I'm going to zoom on out here, and then we're going to be answering these next few questions. Okay, and these 3 questions, number 4, number 5, and number 6. Okay, what are we talking about? We are talking about increasing size, that's atomic radius, increasing electronegativity, or increasing ionization energy of the elements that are here. So before we get into this, what we really need to do is compare the size, ionization energy, and electronegativity on the periodic table. So size, what happens with size? As you go down a group, they get larger. As you go to the left, they get larger. Ionization energy, the exact opposite trend. That is, as you go up, they get larger, and as you go to the right, they get larger. Electronegativity follows the same trend as ionization energy, which is opposite of size. That is, as you go up, they get larger. As you go to the right, they get larger. So if I may put both of these on, or all 3 of these on the same periodic table, let's try to do that. So size is increasing as you go up and increasing as you go to the left. That is size in terms of size. Let's do ionization energy. Ionization energy is increasing as you go to the right, okay, and increasing as you go up. Electronegativity is increasing as you go to the right and increasing as you go up. So you should see that size is opposite that of electronegativity and ionization energy. And electronegativity and ionization energy follow the same pattern. So we're going to be answering questions 4, 5, and 6 kind of together. So what I'm going to do is I'm going to highlight these elements. The first one is going to be beryllium, that is element number 4. Then fluorine, element number 9. Potassium, number 19. Selenium, number 34. And cesium, number 55. So let's find all 5 of those elements here. So we got our periodic table. We're going to zoom on out. So we got the whole thing here. Perfecto. And there we go. So the first one that we are doing is element number 4. That is beryllium. That is right here. The next one is element number 9. That is fluorine. That's right there. Then we have element number 19. That is potassium. Then we have element number 34. That's selenium. And then we have element number 55. That is cesium, just like that. All right. So in terms of size, that is our first question. In terms of size, which one is larger? So wait a second. I think we made a mistake here, and let's see if you can help me correct it. In terms of size, size gets larger as you go down the group, and it gets larger as you go to the left. Okay? Yeah, so make sure that you note that correction right there. Hopefully you caught me on that. Every now and then I like to make a little mistake just so that you can catch me. So just to clarify, ionization energy, electronegativity get larger as you go to the right and up, and size gets larger as you go down and to the left. All right, so let's go back to this here. Hopefully you caught that. And so let's see if we can answer this question. Which one is largest in size? Well, the one that's largest in size is the one that's furthest to the left and furthest down. So that would be cesium. This would be the largest in terms of size. Then the next one that's largest in size, we have either potassium or selenium. And again, the trend is as you go to the left, they get larger. So this is number 1. Then number 2 in terms of size. Then number 3 in terms of size, since selenium is further down in the group than beryllium and fluorine. And beryllium and fluorine are within the same group. So as you go to the left, they get larger. This is number 4, and then this is number 5. So that means fluorine is the smallest in size, and cesium is the largest in terms of size. So we're just going to write these down. The furthest one to the left is the largest. The furthest one to the right is the smallest in terms of size. So let's write those down. So what do we have here? Let's zoom on into this here. The increasing size. That means we need the smallest first. And the smallest was element number 9, and that was fluorine. So that's the smallest. Then the next one was beryllium, and that one would be the next smallest. That is Be, that is element number 4. And then the next one would be selenium. That's Se, and that's element 34. And then the next one would be potassium, and that's element number 19. And then, of course, finally, the largest one, which would be cesium, and that's element number 55. So what we have here is the smallest, fluorine, and then beryllium, then selenium, then potassium, then cesium would be the largest in terms of size. Okay, and that is following the periodic trend that we were following just a moment ago. So hopefully that works well for you. All right, now the next one was we are going to arrange the following atoms, number 5, arrange the following atoms in order of increasing electronegativity. We're talking about the same elements that we just did. So if we zoom on out to that periodic table, size and what is it? Electronegativity are opposite trends. So that means that fluorine is the smallest in size, but the largest in electronegativity. So if I have organized this according to size, what I'm going to do is flip it around and then organize it according to electronegativity. It's that simple. So doing increasing electronegativity, so smallest in terms of electronegativity, and that would be the one that is largest in size. So that's cesium, and that's element 55. Then potassium, that's element number 19. Then selenium, that's element 34. And then beryllium, that's element number 4. And then finally, fluorine, that's element number 9. So all I did was I took largest. What I did is I took this trend right here in terms of size, of increasing size, and I flipped it around, just flipped it, and that will be increasing electronegativity. It's that simple. And in fact, you should see that electronegativity and ionization energy follow the same trend. That is, to the right they get larger, up they get larger. To the right they get larger, up they get larger. So therefore, we're going to repeat the same pattern that we have in problem number 5 with problem number 6. Smallest in ionization energy, which would be cesium, then potassium, then selenium, then beryllium, and then finally fluorine is the largest in terms of ionization energy. That is super cool. All right. So here we go. Now we're going to answer some other questions here. So we're going to scroll this on up here just a bit. Okay, we're going to answer number 7, and it says, what is the trend in size, atomic radius going down a group on the periodic table, and why does this occur? Okay, so we're going to pull out a periodic table, and then we're going to answer this question. And we've already answered this question really in terms of a trend. So size, what happens to size what happens as you going down a group? So as you go down a group, what happens to the size? It increases. So what is the trend in size going down a group? Increasing size down a group. Okay. And then why does this occur? Why does this occur? So the question is why? So here is why. See these numbers right here? N of 1. These are n values, which is called the principal quantum number. N of 2, n of 3, n of 4, n of 5, n of 6, n of 7. As you go down a group, these n values increase, which means you are getting further away from the nucleus. These are the principal quantum number. It's the average distance away from the nucleus. So the, and why does this occur? The n value increases. So that n value increases, meaning that you're getting farther away from the nucleus. So as you get farther away from the nucleus, you get larger. It's that simple. Okay, next problem, number 8. What is the trend in size, atomic radius, within the same period going to the right, and why does this occur? So we're going to pull out a periodic table that we have already used here, and this is just the size periodic table. So we're going to go to the right. So as we go to the right, I said that it gets smaller in terms of size. So size going to the right is smaller, decreasing size to the right. And then the answer to this is, well, so decreasing size to the right. And then the follow-up is, why does this occur? So the why is as follows. So you get smaller and smaller as you go to the right. And here's why. As you go to the right, what's happening to the principal, well, what's happening to the atomic number? The atomic number is increasing. 41, 42, 43, 44, 45, 46, 22, 23, 24, 25, 26, 27, 28. Whichever period you go in, you're going to the right, you're increasing. And that is the effective nuclear charge. That's the protons increases. Okay, so the effective nuclear charge, the number of protons increases as you move to the right, and that draws the electrons in tighter. So as you have more and more positive charge, you're drawing those oppositely charged electrons closer in, and that's why the size decreases going to the right within a periodic table on the periodic table. Okay. Hey, just so you know, just a quick little station break here, a little self-advertisement, if you will. I am the Crazy Hat Chemist, and if you want to know more details as to why these things are occurring, you probably should be watching my videos on honors chemistry or advanced placement chemistry. But this is just a scratching of the surface. So, and of course, I am the Crazy Hat Chemist, and this is where real chemistry happens. There's my logo that my son made, and check this out. This is even better right here. I like this right here. So here we go. I got a little QR code and with my little logo right there, and you can go directly to my YouTube channel if you aren't already there. Like, subscribe, and learn. That's what it's all about. Where real chemistry happens, like, subscribe, and learn. All right, so here we go. Without further ado, let's keep on going on this video here. All right, how is the modern periodic table organized? So what we need to do is we need to pull out our periodic table again and take a look at any one of them. And let's get a new periodic table here. So how is the modern periodic table organized? Real simply, the modern periodic table is organized according to the Z. That is the number of protons, so the atomic number. So this is the principal organization. The primary organization of the periodic table is increasing number of protons, which is the atomic number. So how is the modern periodic table organized? Atomic. Let's zoom in on this. Atomic number. That's equal to the number of protons. Okay. All right, fantastic. All right, then we got a couple other questions here that we didn't really answer up above. We talked about what the trends were, but we didn't talk about what is electronegativity. So number 10 says, what is electronegativity? And electronegativity is the strength of atoms to attract valence electrons in a bond. Again, this is a very simple primary definition, but regardless, that little simple definition works quite well. It's the strength of atoms to attract valence electrons in a bond. And what is ionization energy? Well, ionization energy is the energy to remove an electron from the gaseous state. So if you have the gaseous state of either an atom or an ion, it's the energy to remove that electron from the atom or the ion. Okay? All right, perfect. All right, the next one, number 12, where are the metals and nonmetals located on the periodic table? Well, what we're going to have to do is we're going to have to pull out a periodic table to answer that question. So here we go. Let's pull out a periodic table. So where are the metals and the nonmetals located? So um, I don't, doesn't really matter, but there's this beautiful line on the periodic table that I am using. So I'm just going to highlight this here. Okay, so this line denotes the placement of where the metals and the nonmetals are. So everything to the left of this line are metals. And everything to the right of this line are non-metals. Okay, there is one exclusion to this. Okay, so for example, nonmetals. Nonmetals are to the right of this staircase line. That one example that is to the left of that line is hydrogen. Okay, so all the metals are to the left of the line, and these orange ones are all metals. These ones are all metals. Okay, so you should see that the metals are to the left of the line, the non-metals are to the right. Perfect. Boom. Like, subscribe, learn. Can't get any better than that, huh? I like the slogan. All right, so now what we're going to do is we're going to check off that answer here. So we've labeled that. Okay, now we're going to scroll this baby on up. And we're going to answer this next question here. List the defining characteristics of metals. So defining characteristics of metals. And this is in my lecture. So where are you getting this from? In my lecture, by the way. Okay. There is no particular order to this. It doesn't matter the order. We just need to know that the characteristics of metals are these following set of characteristics. So solids at room temperature. And that's denoted as RT sometimes. And the one exception to this is mercury. So the one exception to this is mercury is actually something that is a liquid at room temperature and pressure, but that is the only exception. Okay, and then the next one would be high luster. Metals have high luster. And then you may ask, well, what is luster? Luster is shiny. So, for example, this little weight right here, it is quite shiny. This is a metal. This right here, this weight right here is also a metal. It is quite shiny, and metals have high luster. They are very shiny. Okay. The next one here of a characteristic is they are conductors of heat. So they are conductors of heat. Metals are conductors of heat. And then next, they are conductors of electricity. Metals are conductors of electricity. Also, metals are malleable and metals are ductile. Malleable and ductile mean that metals can be hammered out into sheets, like aluminum foil, for example, or they can be drawn into wires, like the wires within your home or apartment, so that they can conduct electricity. Metals also have high melting points. And that actually goes right back to point A, which means that they're solids at room temperature and pressure. The next one is that they have high densities. And that means that they are solids at room temperature and pressure as well, effectively. All right, and let's see here. We have another follow-up question here at the bottom, and it says, right at the bottom, it says, what are the characteristics of nonmetals in relationship to metals? They are the opposite. So they are the reverse. So for example, nonmetals, they would not necessarily be solids at room temperature and pressure. There's many that are gases and liquids. They do not have high luster, meaning they have low luster. You cannot shine or polish a nonmetal. They do not conduct heat. They do not conduct electricity. They are not malleable. They are very brittle. They cannot be drawn into wires. They have low melting points and they have low densities. So they share the opposite in terms of characteristics. And a little bit of selfless advertisement. Yet again, I am the crazy hat chemist, and please, I greatly appreciate you watching my videos. I truly appreciate you watching my videos. And please like, subscribe, and learn. I'm really about teaching you real chemistry, and I'm not sure what everybody else is going for nowadays, but I'm going for the real chemistry. So let's see what we got. All right. So what we need to do is we need to flip this worksheet to the other side so that we do the reverse of this worksheet, or the back side of this reversing worksheet. And so here we go. We got some more problems to do. Remember, this is kind of a cumulative review of periodic trends in chemistry. That's what we're doing here, folks. And I am the crazy cat chemist, and please like, subscribe, and you will learn. Okay, so let's see here. We're going to go for our next question here, and our next question is, which element in each pair has the smaller radius? We got boron or fluorine. And so I'm going to pull out a periodic table, and we're going to see if we can hammer this out here. That's number 5 or number 9. So we're going to zoom on. No, we can do this right here. Number 5 or number 9? Which one is smaller in terms of size? Okay. And so the trend in size is as you go to the right, they get smaller. So the one that's to the right is smaller, and that's fluorine. So which one is smaller? Fluorine, because it's more to the right. Excellent. Okay, that's the actual trend. Okay, and then now our next one is element number 7, nitrogen, or element 33, arsenic. So number 7, nitrogen, or number 33, arsenic. Which one is smaller in terms of size? And the trend in terms of size is as you go down a group, they get bigger. So therefore, nitrogen, which is higher up than arsenic, would be the smaller one. So smaller one in terms of size is nitrogen. Bingo. All right. Now the next question here, number 16, is which element in each pair has the smaller first ionization energy? Okay, smaller ionization energy. Now remember, this is opposite that of size. So what we can do actually is just reverse what we have here. And so the answer is going to be right here, and the answer is going to be right here. But we should verify both these in terms of their smaller ionization energies. Okay, so ionization energies go as follows. We are going to compare the boron and the fluorine, and ionization energies increase as you go to the right. So the smaller one would be the boron. Is that correct? Yes, that is correct. Between nitrogen and arsenic, the ionization energy increases as you go to the right, and up it increases. So the smaller one would be the arsenic, and yep, that is correct. Perfect. All right. Now, which one has the smaller electronegativity value of each pair? And the electronegativity and ionization energy follow the same trend. So theoretically, we should be able to answer these just like that, which is opposite that of size. And let's make sure that that is the case as well. So again, we're looking at boron or fluorine. Which one is smaller in electronegativity? Well, as you go to the right, they're larger. Fluorine is actually the largest electronegative element there is. Okay, so it would be certainly the boron. Okay, and then arsenic and nitrogen. And as you go up a group, you increase in electronegativity. Fluorine is the most electronegative. So one that's smaller in electronegativity is arsenic. That is held true there as well. Perfect. All right. Let's see here. Let's do another one. Okay, the next one is arrange the following atoms in order of increasing size, that's atomic radius. And we have lithium, chlorine, yttrium, and barium. And so what we're going to do is organize these in increasing size. So let's give this one a try. So we've got, let's see here, which elements that we're going to look at. Let's zoom on out, and then I'm going to highlight these ones so that we have these ones available to us. So the first one was element number 3, that is lithium. The next one is element number 17, that is chlorine. And then number 39, that's a yttrium. And then number 56, that's barium. Okay, so what we're trying to do, let's just verify the question here. Increasing size, increasing size. So the one that in terms of size, as you go down a group, they're larger. As you go to the right, they're smaller. But as you go to the left, they're larger. So the largest one is right here. So that's number 1, that's the biggest. Then number 2, that's the next biggest. And then we have this going on. So the next one that is largest in size would be, as you remember, as you go down a group, they get bigger, and lithium is higher up. So it's going to be the smallest one. And chlorine would be the next one. So we're going to write this in order of increasing size. So that means that we're going to have the smallest one first. That is lithium at element number 3. That is the smallest. Then we are going to have the chlorine, and that's element number 17. And then we have yttrium, that's element number 39. And then we have barium, and that's element number 56. Perfect. And I'm going to zoom in on that because that's kind of hard to see, I'm sure. Okay. Let's see. There we go. Now you can see the question and the answer. Perfecto. Okay, then the next problem here is that we are going to do increasing electronegativity, and we have the same set of 4 elements. And remember that atomic size and electronegativity are exactly opposite. So what I'm going to do is I'm going to take this atomic size and I'm going to flip it around. So barium, number 56, is first. That is the smallest. Then 39, that's yttrium, and then chlorine, and that's 17, and then lithium, number 3. And then ionization energy and electronegativity follow the same trend, so I'm going to just duplicate that. There we go, just like that. And 17, and then 3 for lithium. So, by the way, just for the curious-minded and the critical chemist, if you are, and if you are in a higher level of chemistry, I am just doing based on trends, just flat out trends. If you were to look up the values of electronegativity or ionization energy, they might not be in this same order. In fact, I bet you they won't be. But we're talking about trends. These are not absolutes, just trends. Okay, folks? All right, just making sure that you know what that means. Okay, the next question here are list the diatomic elements. So what are the diatomic elements? So let's get ourselves a periodic table, and then we can write down the diatomics. All right, we got ourselves a new periodic table, and diatomic. Di means 2 atom molecules. Okay, so 2 atom molecules are the diatomics. So here they are. I'm going to show them to you on a periodic table, but I'm going to fold the periodic table just a little bit and you'll be able to see them very nicely. Okay. It will all make sense, hopefully. Here we go. Just a little folding of the periodic table. Sorry for the delay, but here we go. So what are the diatomics? They are the following elements: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. So these are the 7 diatomic elements right there. You notice that it is in the shape of a 7, and nitrogen is the most abundant gas in our atmosphere, and that's where we start. And then we go for oxygen, fluorine, chlorine, bromine, and iodine. 1, 2, 3, 4, 5, 6, and then jumped over to hydrogen. So I'm going to write these down here. So I have hydrogen, that's element number 1. Then I have nitrogen, that's element number 7. Oxygen, that's element number 8. Fluorine, that's number 9. Chlorine, that's number 17. Iodine, bromine would be next probably, and then iodine. Bromine is number 35. And then iodine is number 53. Okay, those are the 7 diatomic elements. Okay, perfect. All right, and the next question is, what list the metalloids or the semimetals? So earlier in this lecture, I had certainly talked about this little line that's distinguishing between the metals and the nonmetals. So this line right here is important to distinguish the metals on the nonmetals. And so what we're going to do is we're going to effectively count to 7, but go back and forth on either side of this line. There is one element that we are going to skip, and that is aluminum, because we know aluminum is a metal. So what are the 7 metalloids? 1, 2, 3, 4, 5, 6, and one of these is 7. So that is boron, silicon, germanium, arsenic, antimony, tellurium, polonium, or astatine. So I'm going to write those down. That is B for boron. That's number 5. Silicone, and that's number 14. Germanium, and that's number 32. Arsenic, and that is number 33. Antimony, that is number 51. Tellurium, that is number 52. And it's either polonium at 84 or astatine at 85. And there's a little bit of like, well, I'm not sure which one it is kind of thing, and that's okay. Us chemists haven't decided which ones they are. Okay. Okay, fantastic. There are some more questions here on this worksheet here, but I think we're going to have to reserve that for another video here to tidy this up. We are really close to this, but we are kind of running out of time here that I have at this moment in time, if you will. No, let's see if we can keep on going. So remember, like, subscribe, and learn. That's what we're all about. All right, so the next one here, we're going to scroll this out here just a bit, and we're going to say, what are the predicted charges of elements on the periodic table? Label as many as you can on the periodic table. So what are the predicted charges on the periodic table? So we're going to pull out a periodic table, and we are going to write these out. Okay, so let's make sure that you got your periodic table. It's as close as possible. Here we go. Predicted charges on the periodic table. This is going to be a 1+ charge in this column group, 2+, 3+, 4+, 5+. And what is the Roman numeral for 5? It's a V. Okay, so 1, 2, 3, 4, and 5 in these columns. Then what we're going to do is we're going to count 5 elements. 1, 2, 3, 4, and 5. These 5 elements have the following 2 charges of a 2+ and a 3+. Okay, then you've been speeding down the highway too fast at 2 and 3, and you gotta slow down because who do you see behind you? A copper. So copper has a 1 and a 2. So notice that you decrease these speeds by 1 each. Okay, silver has a 1 plus charge, zinc has a 2 plus charge, and aluminum has a 3 plus charge. There's a diagonal pattern there. You notice that scandium and yttrium have the same 3 plus charge. Beryllium, magnesium, calcium, strontium, barium, and radium have the same 2 plus charge. So therefore, cadmium and zinc have the same 2 plus charge. Gold has 2 charges of a 1, which is common between the copper and the silver, and it is worth more. So of course it has the higher charge of the 3, which is a 3 plus. Everything in this column here would be a 3 plus charge in this column. We have mercury, and there are 2 different charges of mercury. There's a 1 plus and a 2 plus. We got 2 unusual elements right over here, and that is tin and lead. And both of them have a 2 plus and a 4 plus for both of them. There's a 2 and a 4 for tin and a 2 and a 4 for lead. Now notice that we are using this orange staircase line, this orange staircase line to differentiate the metals that I just talked about, which lose electrons, and that's why they form positive charges. The noble gases don't have a charge. The next group here, -1, the halogens, -2, and then a -3. All right. That gets you the periodic trend charges on the periodic table. It's a periodic table because it's periodically changing. It has periodic trends. Holy moly, that's awesome. All right, so that is it for that problem. Perfecto. And now that we have answered number 23. Number 24, what are the number of valence electrons for each group on the periodic table? Label as many as you can. All right. So what we're going to do with this one here is we are going to do the following. So we're going to take our periodic table and from previous videos on electron configurations, we should understand S, P, D, and F. So what grade do you not want to get in chemistry? An F. So I'm going to take the Fs and I'm going to fold them out like thus. What other grade do you not want to get in chemistry? A D. So let's get rid of the Ds. Okay. Let's see if we can get rid of the Ds. And what kind of grades are you left with? Well, satisfactory passing grades. That's S and P type orbitals. And the number of valence electrons, that's valence, not valence. 1, 2, 3, 4, 5, 6, 7, 8, excluding helium. Notice that all of these have that same number with an A right above it. So you really can't go wrong with the periodic table that I'm using for this activity. Okay. And then is, well, in the D's and the F's, which is this block of elements, and I'm going to draw a cutesy little picture here for you. Not a very good picture, but you should see that this looks like what? A boot. And so that's why all of these are B's because they're in the boot. So how many boots would you wear? 2 boots. So how many valence electrons if it's a D or an F? 2 valence electrons, 2 boots. Booyah. That answers that question. So now we have answered the question as to where the number of valence electrons are and what they are. Okay, now the next one is we need to label the periodic table with all kinds of things here. So we're going to pull out a new periodic table and then follow along here. So zooming on out, we got to do certain sections here. So the first one are the alkali metals. So what are the alkali metals? They are in group 1. Okay, the next one are the alkaline earth metals. Alkaline earth metals are group 2. Okay, so we got the alkaline metals, the alkaline earth metals, the transition metals. The transition metals are right here. That is in this entire section right here, which is the D block. The halogens, that is right here. And the noble gases, that's right there. And what else do we have here? We have the metals and the nonmetals. We've already done that. We have the inner transition elements. So the F block right here, inner transition metals. That's right there. Then we have the lanthanides. That is this group. It's right next to that. And then we have the actinides. And that's this group right here. So lanthanides, actinides. And then one last grouping, and those are the representative elements. And so what we're going to do is we're going to take our periodic table, fold out the D's and the F's. And what do you have? These right here are the representative elements. Representative, or main group elements. So main group elements, representative elements are the S's and P's. Cool. Okay, awesome. Labeled up that periodic table. Let's see if we can hammer out another question here. Okay, what are the horizontal sections on the periodic table called? The horizontal sections? Well, those are periods. I have mentioned that a number of times. What are the vertical columns on the periodic table called? Those are groups or families. And let's see what else we've got right here. What is a cation and what is an anion? A cation is an ion with a positive charge. And what is an anion? An ion with a negative charge. And that is cations have lost electrons and anions have gained electrons. Which element would form a cation and why? Cation would be that titanium because it's a metal. And which would form an anion and why? Phosphorus because it's a non-metal. Fantastic. I think we just did this. Please like, subscribe, learn. This is where real chemistry happens, and I think we made it just before the bell. I greatly appreciate your time. Please like, subscribe, and learn. And thank you very much. Have a delightful day. Bye for now.